Saturn looks permanent from Earth. Its rings seem almost like part of the planet itself, a feature that has always been there and always will be. But that is not what the evidence suggests. Material from the rings is falling into Saturn's atmosphere right now. Some of it arrives as electrically charged water products. Some was detected by Cassini as a much more complicated mixture of gas and tiny particles. In other words, the rings are not simply circling Saturn. They are interacting with it, feeding material into the planet, and slowly changing in the process. So the real question is not just what Saturn's rings are made of. It is this: are we looking at a temporary phase in the life of the planet, one that future Saturn may no longer have? The first thing to forget is the idea of a solid ring. Saturn is surrounded by an enormous swarm of separate particles, most of them dominated by water ice, each following its own orbit around the planet. Some are tiny grains, others are much larger fragments. Together, they create the smooth bands we see from a distance. But up close, the system is constantly being sculpted by collisions, gravity, resonances with moons, and electromagnetic forces. Even the gaps and narrow ringlets are part of this motion. The rings may look geometrically perfect, but they are physically restless. Particles collide, break apart, clump temporarily, migrate, and exchange material with the rest of the Saturn system. That dynamism is the key to understanding why the rings can also lose matter. Long before Cassini's final plunge, astronomers had evidence that the rings were connected to Saturn's atmosphere. Infrared observations revealed unusual patterns in the planet's ionosphere. Those patterns matched magnetic field lines that connect Saturn to specific regions of the rings. The explanation was extraordinary. Charged water products were being removed from the rings and guided along the magnetic field toward the planet. Scientists called it ring rain. This rain is not like weather on Earth. It is a stream of microscopic material moving from orbit into the upper atmosphere, where it can change the local chemistry and reduce electron densities. The important point is that Saturn's rings are not isolated decorations. They are physically coupled to the planet below them. Then, in 2017, Cassini did something no spacecraft had done before. During its grand finale, it completed 22 dives through the narrow region between Saturn's cloud tops and the inner edge of the rings. Instruments aboard the spacecraft sampled material in this environment directly. Scientists expected water because water ice dominates the rings. But Cassini also detected methane, ammonia, carbon monoxide or nitrogen-bearing material, carbon dioxide, and complex organic compounds. The inflow was also surprisingly large in some measurements. That changed the picture. Ring rain was no longer only a distant effect inferred from the atmosphere. Cassini had flown through the region where ring material was entering Saturn and measured part of that exchange at close range. This is where the story becomes less certain. NASA has publicized estimates suggesting that if some measured loss rates continued, Saturn could lose its rings on a timescale of roughly 100 million years, or a few hundred million years under other assumptions. That sounds precise, but it is not a countdown clock. Different instruments measured different components of the inflow, and later atmospheric modeling found a puzzle. If the very large 2017 influx had been continuing steadily for a long time, Saturn's atmosphere should show stronger chemical consequences than we actually see. One possibility is that Cassini caught a temporary episode of unusually heavy inflow. Another is that much of the material arrives as extremely small dust particles. The rings are losing mass. The exact long-term rate is still uncertain. For years, one of the strongest arguments for young rings was their appearance. Saturn's main rings are remarkably bright and rich in clean water ice. Over billions of years, micrometeorites should have added darker, non-icy material. Cassini also measured the mass of the rings, and studies of the incoming micrometeorite flux strengthened the case that the main rings may be only a few hundred million years old, extraordinarily young compared with Saturn itself. But the debate is not finished. A 2025 study modeled what happens when high-speed micrometeorites strike icy ring particles and found that much of the contaminating material may be vaporized or ejected instead of sticking. If that self-cleaning effect is efficient, the rings could look young even if they are much older. their brightness may not be a simple clock after all. And if the rings really are young, where did they come from? One striking hypothesis proposes that Saturn once had another large moon. Researchers named it Chrysalis. In a 2022 model, changes in the Saturnian moon system could have destabilized its orbit roughly 100 to 200 million years ago, sending it dangerously close to Saturn. The planet's tidal forces may then have torn the moon apart, with some of its icy material remaining in orbit and eventually becoming the rings. In 2026, new simulations showed that under the right kind of close encounter, Saturn could preferentially strip the icy mantle from such a moon and produce ring material with properties similar to what we see today. Chrysalis is still a hypothesis, not a discovery, but it captures the deeper lesson. Saturn's rings may be beautiful precisely because they are temporary. We may be seeing the planet during one remarkable chapter of a much longer story. If you enjoy discovering what happens in the most distant corners of the universe, how our planet formed, how life began, and how people really lived in the ancient world, subscribe. We're only just getting started.